Okay, so tonight we're going to be looking at Module 7, which is going to be CAM design. So as we look here, our module looks very similar to what we've had in the past. Learning plan wise, we're going to be looking at Chapter 9. We'll be working through this PowerPoint this evening. I will be recording. We are going to split this into 2 lectures. Tonight we're going to look at kind of the introduction to CAMs, looking at what we call displacement diagrams. And then the next time we meet, using displacement diagrams to create the actual CAM profile. So it works out really nice to kind of divide it into 2. So I'll put the session recordings out there as they become available. We do have some practice problems to do. If you click on the Module 7 practice problems, you're going to see that there's 3 examples here. We will be doing these 3 tonight. Okay, so at the end of tonight, even though we have more to go through the next time we're together, they just don't lend themselves as well to practice problems. So I just kind of picked these 3. Also remember that there are 2 little questions here. What did I learn? And I went back to what do you still need practice on? So make sure that you answer those. And then your assignment number 7 is just going to be 4 problems. As you can see, they're 20 points each, so they are a little bit more involved, and we'll get to that after we get through the lecture that we have tonight. So the first 2 are going to be something you'll be able to do this evening or after this evening, and then the next 2 are going to be after the next lecture that we have. Okay. So what I'm going to do is we're going to get started by going to the PowerPoint presentation and looking at that to get started here. Okay. So chapter 9 starts on page 223 in your book, and we're going to be looking at CAM design. So in this unit, in this module, we're going to be, our objectives here are going to be to identify different types of CAMs and followers. Also, we want to make sure that you understand the benefits of different types of follower motion and different schemes, really like when you're going to be using them and when you wouldn't. Ultimately, we're going to be able to construct a displacement diagram for a CAM follower and construct the profile of a disc cam using that displacement diagram information. So these last 2 are really what the focus is for the assignments that you're going to be having. So first of all, a cam is going to accept an input motion, and that input motion most often is going to be in a rotational type of a direction. So many times it's going to be a cam that is going to be on a shaft. It is going to be the input motion then for a follower. The follower would be considered the output of the motion, but there is some cams that have a little bit different arrangement, and we'll look at one that is a little bit different. Now, as we look at figure 9.1, this is a very classic example of an application of a cam and a follower. And you're going to notice here that this is an engine valve train. So if we kind of start at the bottom here, here is the valve that is going to basically move up and down vertically to open and close the combustion chamber. And then it's connected to a valve stem that then has a spring around it, which on the end of the valve stem then comes in contact with our rocker arm, okay? That rocker arm pivots here, and it is controlled in motion by the camshaft that is directly above it, okay? This spring right here ensures that as the valve stem pushes up on that rocker arm, it is always in contact with the profile of our cam. On our cam or our cam shaft, the shaft is the part that is rotating about the center in the middle here. The cam is the irregular profile that we see here, and that irregular portion there is considered what we call a lobe. As this rotates around, that lobe is going to, if you would, push the rocker arm down, and then as it rotates past it, it's going to come back up again. And what that does for us is, based on that one revolution, it is imparting this motion. So when it's around the smaller portion, it's going to stay in the same position it is at this time. But then as that lobe comes around and it imparts the motion of that rocker arm going down, the valve is going to go down during that time frame, and then it's going to go back up as it passes over that lobe. Cams are all about timing. Okay, so what we're going to be doing is we are going to be looking at motion that we need for one revolution on that camshaft, and then how much time we need to do each one of the motions that's required. Something that we see here that I think is important to mention at least one time here, and then we'll talk about it again, is that when we have this arrangement of cam and follower, okay, this would be the cam, this would be the follower. The cam, as we said, is going to be the input motion. The follower is the output motion, all right? The follower has to always be in contact with the profile of the cam. If it is not following the motion that is prescribed or that is being designed for that, okay? So that is why we have things like springs that are going to ensure that that follower is always in contact with the profile of the cam, okay? All right. Now, cams can impart very distinct motions of a follower. So sometimes we want things to move, sometimes we want them to stay in place, or we want them what we call dwell. Many times we're going to be referring to motion as rise, and then dwells and falls. Okay, so those three are going to be describing what we're going to be doing. And then in that, we're also going to be looking at different types of what we call motion schemes. So how we're actually going to achieve that. So we'll see that as we kind of get started here in the beginnings of this chapter. What's nice about cams is that they're used a lot in, for instance, factory automation because they can sequence displacements in a very cost-effective way. So we end up having, I mean, for the most part, we want this rocker arm to move or pivot up and down as that cam shaft goes around. We're taking a circular motion or rotational motion and we're converting it into, although this is pivoting, ultimately it's a linear motion that we are translating it into. And if we look here, it's pretty simplistic. There aren't a whole lot of parts, which makes it attractive for building it into designs. So it's something that we always want to consider when we're trying to achieve different types of motion. Now, there are different types of cams. There's some custom cams, but what we're going to be designing is going to be plate or disc cams. So if we look underneath and we turn the page here to page 224, at the top here, they have a couple different types of what they call custom cams. So the first one that we have here, the diameter that we see would actually interact with a shaft. You'll also see a keyway there, and that keyway is then going to ensure that through the use of a key in the shaft, that we're going to be able to rotate that at the same RPMs. This irregular shape that we see here, the center of rotation is going to be at the center of the shaft. So then this part would be kind of that control in contact with the follower that is then going to move in, out, up, down, whatever it might be. And then we see a couple other different kinds here. Now, in the examples and the practice that you're going to get, we are going to be focusing on a plate cam, okay? So a plate cam, as you can see here, its center of rotation is going to be where we see this center line here. This is going to be a hub then that is going to have a shaft going through the middle. And again, keyed so that we can ensure that the shaft and the cam are going to have the same rotational, speed. Now, the portion around the outside, this profile, is the actual cam itself, and that is what is going to impart the motion. In this case, it is in contact with a roller pivoting follower. So the follower is pivoting because here we have a pin for which it's going to pivot, and then it's in contact with the surface of the plate cam, the outside of that cam profile, with that roller that's on the end there. So a very common application of a cam and a follower arrangement. So again, the cam is always going to be our input. The follower is going to be our output. As we look to the right here, this is a cylindrical cam. So a little bit different arrangement, actually a lot different arrangement. Here we have a cylinder. This is kind of like the shaft portion, but instead of having our cam profile that the follower is in contact with, there's actually a groove that is going to be, if you would, carved into the surface of that cylinder, for which the follower will then follow and then go in and out as it follows the curve that's in there. And then lastly, we have what we call a linear cam. This is where our cam input is actually going horizontally back and forth. And then the follower, because the peg is in the groove that we see here, is going to then go up and down. Okay, so a couple different ways, but we're going to be focusing on the classic, if you would, plate cam arrangement here. Now, just as there are different types of cams, there are different types of followers. And the different types of followers that we have here, follower types, if you would, are going to be inline, offset, and pivoting. And we're going to see those on that same page, but in the second column over here. So the first type that we have here is called an inline follower. If we look at the follower itself, so the cam is here, the follower is here. As we look at that output, you'll notice that the center line of the travel, which is going to be vertically on this follower, is in line and would actually extend and go through the center line of the rotation or the shaft rotation. Okay. As we look down below here, we have another cam follower. It also is going to be vertical, as we can see. But if we extend its center line down, notice that it is offset from the rotation of the actual cam, the center of rotation of the shaft. Okay. And then the third type of follower, and we see it in both cases in part B and part D here, is a pivoting follower. And that's where we have it on an arm that is going to pivot about a pin or a center, as we see here. So those are inline, offset, okay, and pivoting. Those are like the three main types of followers. Now, as far as follower shape, this can take a lot of different forms, but the four main types we see in that same illustration. So the first one here is going to be a knife edge. Now, in any one of these arrangements, we can pretty much put any one of these different types of cam follower shapes. So the knife edge is simply, it comes to a point almost like a pencil, and it is going to have then contact with the profile of the cam. Not used all that often for a couple of reasons. Number one, there's a lot of stress concentration at the end of that point. It's kind of like a pencil. It's going to kind of dull, relatively fast unless you have some sort of a treatment on it. And it can make grooves in just one area around that profile of that shaft. So unless it's kind of slow moving, or intermittent use, it's not the most popular one, but it's a simple, kind. The next one that we have here is going to be a roller, actually probably one of the most popular. The roller, as you can see here, is going to have contact with the plate cam profile. And what's nice about that is typically we don't maybe see those details, but the center of that roller is usually going to be a ball bearing. Okay, so very low friction, free flowing, really, really nice and smooth operation. The next one that we see here is going to be a flat face follower. So kind of similar to the knife edge, except now we've got more surface contact. So not as much chance for grooving, if you would, or stress concentration, but there definitely is going to be more friction than the roller type. And then lastly, we have a spherical end. Again, it's spherical on its shape here. It comes in contact with the profile. Does have that friction because you're going to have surface on surface, but again, another option for the type of follower that you would have, like a shape. So again, these are four different types, common types, but it can really take a lot of different forms. Now, motion of a cam follower. The motion is going to either be translating, meaning it's going to be linear, or it's going to be swinging or pivoting. And we see that again in the illustrations here. So the linears are going to be the verticals here in A and in C. Okay, the followers, as we can see, are going to be going vertical. So, and they can go horizontal, or they can, go on the bottom side. So it's not constrained. These can be at an angle, but it's really going to be that the follower is going to have linear motion where the cam is going to be rotational. On the other hand, for the pivoting over here, you can see how that motion is different. Now, it's kind of linear, but it is technically pivoting around a fixed center. So depending on how long that arm is going to be either, more of a radius, or it's going to be more linear. We already talked about follower position inline or offset, and that is really just extending the travel center of the follower to see if it goes through the center of rotation of the cam. If it does, it's an inline. If it doesn't, it's offset. We already talked about the different follower shapes, so I'm going to skip over that. And then now we're going to be looking at the motion. So as we said earlier, when we look at cam motion, we are looking at what we need to happen in one rotation of that cam going around, okay? And what we're going to have is we are going to determine what are the different motions we need, and we're going to add that up and we're going to have a total time. So we're going to find that the total time is going to be one cycle, a complete cycle, or one revolution. And it is going to be broken down into whatever the different prescribed motions are that you need. So then we would have a time associated with the first motion, a time with the second motion, the third, and so on, however many things that you need to happen in that one revolution. The ones that you're going to be doing are anywhere from 3 to 4 different times or different types of motion in one revolution, okay? Now, the next thing that you're going to need to do is you're going to need to determine what the angular speed is of the actual cam itself. And that's going to be where if I take one revolution and I divide it by the total time for which I need to do the motion that's prescribed, I can get what my angular speed is going to be of my cam. So we'll be calculating that. And then lastly, the other thing that we need to do is we need to calculate the number of degrees per individual motion. So when we start looking at the different motions that are required during the different times, then we want to equate that to how many degrees of a full revolution do each one of those take up. Okay, so we call that beta. Now, we're going to be looking at example 1, and we're going to kind of get started on some of these items. So I'm going to go underneath my camera, and we're going to turn the page, and we're going to look at our first example, which is example 9.1. Okay, oops, maybe a little bit out. Okay, now the full problem statement here is we have a cam. It's going to be used for a platform that is going to be repeatedly lifting boxes from one level to another. Okay, the machine is shown down here. So you're going to see that down below is going to be our cam. It is rotating on a shaft. Okay. Now, as we look here, you're going to notice it looks to me like this is a roller that is in contact with that profile. We have a spring ensuring that it indeed is doing that. So as this rotates around, okay, and this larger lobe comes up, this is going to go up and it's going to go down. And it needs to go a distance so that as we move this up, that box is going to be able to be at the height of the other platform, okay? So you would, do some measurements here and you would figure out, how high that has to go and how much time we would want for that to take. And that's what we have down here. We have the prescribed motion, if you would. So the first step is we are going to rise 2 inches. So that would mean that this distance from here to here is 2 inches, okay, that we want that to go up. And we want that to take 1.2 seconds. Then we're going to dwell. We're going to stay in that position. Dwell just means we're going to stay right there as we rose, and we're going to stay at that same position for 0.3 seconds. Then we're going to fall 1 inch in 0.9 seconds. We're going to dwell for another 0.6 seconds. And then we're going to fall another inch in 0.9 seconds. Now, as we look here, something that you have to be aware of for any motion that is prescribed for a cam, however many rises there are, however much rise, however much distance and rise that you have to come back down in your fall. So in this case, we have a rise of a total of 2 inches. And notice that our first fall is 1 inch, but then we have a second fall of another inch. The falls have to equal your rises. You don't have to do any one of these in one operation if you would. You can do it in stages as we see the fall happen, but we have to look at what are the total rises have to equal the total falls. And then as we look here, this is the amount of time. If we add up the total time here, that's going to be the time that it takes for one revolution of our cam. So step number one here is to determine what that time is for a full cycle. So this is our first practice problem. So you're going to want to start this off by calling this example 9.1. And our step number one here is going to be, we're going to determine what the total time is. Now, capital T is the total time. The summation symbol is in front of there because we're going to be adding up the individual times. And I'm not sure why they use the sub I here. I'm not sure. It's just what they use. So we're going to say equal to, and we're going to take time one, okay, which is going to be step number one. Okay, that's going to be our rise of 2 inches in 1.2 seconds. So the time here is 1.2 seconds plus time 2, which is going to be the dwell of 0.3 seconds. Okay, time 3 is going to be another fall plus time 4, a dwell, plus a time 5, which is going to be the rest of the fall. Okay. So now what we're going to do, this is our equation, if you would, in variable form. So now we're going to take each one of the times associated with each one of those steps, and we're going to add them together. So the first one is 1.2 seconds plus 0.3 seconds plus 0.9 seconds, 0.6 seconds, and the last one is 0.9 seconds. Okay. So we're going to add each one of those together, and our total time then for one revolution, one cycle, we say, is going to be, it looks like, is it 3.9 seconds? Okay. So make sure you get that same value. Now, I'm not going to put a box around this because this isn't something they're asking for. They want us to determine, they want us to plot the displacement diagram. We'll get there in just a little bit, but they want us to determine what is the speed of the cam, okay? Now, remember, the cam is going to be on the shaft. It's going to be rotating. So the second step that we're going to have here is we're going to determine the angular velocity of our cam, okay? And that's going to be equal to 1 revolution divided by the total time for 1 revolution, okay? So we determined that our total time was 3.9 seconds. So this is going to be 1 revolution divided by 3.9 seconds. So the angular velocity of our cam is what? What do we get? Everybody should have their calculators out and doing this along with me. What is it? 0.2564, did you get? Well, that's what we're going to write right now because we're in revolutions per second. And that number will come in handy in a little bit. So we do want to calculate that. But if we're reporting it, as Lex was questioning it, we do need to change it to revolutions per minute, right? So 1 minute is equal to 60 seconds. So my seconds will cancel out. So I will say that my angular velocity of my cam is what? How many revolutions per minute? 15.38. That sounds correct. And that's going to be RPMs. Okay. Now this I would put a box around because they were asking us for what is the angular velocity of our cam. And yes, we would report it in RPMs if we were sharing that with somebody or picking a motor or, you know, a means of getting that to rotate for that angular velocity. Okay. Then what we want to do is we know that we're going to be taking a total time of 3.9 seconds to rotate 1 revolution, okay? Now, each one of our steps here, each one of our 5 steps here is going to take up a portion of degrees in that 1 revolution, right? So we now want to figure out is for each one of those steps, what is what we call the beta? Okay, how many degrees equates to that one step? Okay, so we are going to be calculating then a beta 1 through 5 for each one of our steps. So our beta 1, which is the amount of degrees that it's going to take to rise 2 inches in 1.2 seconds, is going to be equal to our cam, angular velocity, times the corresponding T1, the amount of time for our first step here. Now, this is where if we look back up to the top, we know that our times are in seconds up here. So we are not going to multiply by the RPMs. We're going to multiply by the revolutions per second. Okay. So we are going to do our W of our cam, or angular velocity of our cam, of the 0.2564 revolutions per second times 1.2 seconds. Okay. So that means our seconds are going to cancel. And now we have our beta 1 in revolutions. How many revolutions, or how much of a revolution are we going to get for that first beta 1? 0.3077. Is that what you guys got? Revolutions. Okay. But now, as I said earlier, revolutions is nice, but we want to know how many degrees it's going to take out of 360. So we just need to do a quick conversion here. We know that 1 revolution is equal to 360 degrees, right? So we can cancel out revolutions. And what does our beta 1 come out to be? Yep, 110.76, right? Degrees. And that's equal to beta 1. All right. So what that means is our first step is going to take up 110.76 degrees of that 360 in 1 revolution. Okay. Now we want to figure out what beta 2 is, beta 3, beta 4, and beta 5. And then we're going to add those up and make sure that they all add to 360 to make sure that we did it correctly. So now let's do beta 2. Beta 2 is also going to be the W of the cam, but this time it's going to be times the time 2. Okay. So same number here, 0.2564 revolutions per second, but this time our time 2 for that dwell is 0.3 seconds. Okay. So beta 2 should get 0.077 revolutions. Is that right? I don't think so.
Oh, yeah, 0.077.
0.077. Okay. And then we know that 1 revolution is 360 degrees. So revolutions cancel. We're left with degrees. And what do you get for beta 2? 27.6 degrees. Okay. So go ahead and do that for 3, 4, and 5. Okay. Do that for 3, 4, and 5. Beta 3, 4, and 5. I'll kind of do mine on the side here and then we can compare. I don't like mechanical pencils. They always break on me, but my other pencil was kind of dull. T3. So for 3, 4, and 5, you should get 83.07-ish for beta 3, 55.38 for beta 4, and then the same thing for beta 5 as beta 3, so 83.07. Now, what you want to do is once you get those, add them all up to ensure that they add to 360. This is a check that I require you to do, okay, on your problems, because if you miss one or something like that, now right here is where you can catch that. So go ahead and add up all 5 to be sure that they add to 360 degrees. Mine comes up to 359.88. So 360 is equal to 360. Okay. All right. Now, what did we just calculate? Okay, all of these betas. So what I want to do is I want to look at the displacement diagram. I just have some things that are on here I want to erase before we look at mine under my camera here. Okay. So I'll probably go back and right over the top again. Now, what we've done is the first 3 steps of this example. The 4th step is to create the displacement diagram. Now, we don't have quite enough information to create the displacement diagram. They created one here for you. So I want to point out the elements that are here because we're not going to be creating these for the practice problems that we do, but you will be creating them in AutoCAD for the assignments that you have. So you're going to have 2 displacement diagrams to create, and you start each problem exactly those first 3 steps that we just took. Okay. So let's look at a displacement diagram and the elements that we are going to see here. So the displacement diagram is going to have an X and a Y axis. The y-axis is going to be follower displacement. So this is where we look at what is the total rise that we saw here, okay? In this case, it was right away in step number 1, and it was a total of 2 inches, okay? So notice that our scale here identifies 2 inches as the top, and we're going to notice that that is the highest point on our curve as well, okay? How far that displacement is going. Notice that it's called follower displacement and it has the units here. So when you create your chart, you have to have these labels and units on the axes, okay? Let's look at the horizontal axis or the x-axis here. There's a lot going on there. First of all, the top line along the immediate bottom of our displacement diagram, this is called cam rotation. And notice that the units here are in degrees, okay? Now, on one cam rotation, it's going to be 360 degrees. So notice that it's going to start out at 0. And then they put some of the milestones in here, 90, 180, 270, and 360 is the very end. Okay. Now, directly underneath that, you're going to notice that they have the betas. Beta 1, beta 2, 3, 4, and 5. Each one of those segments corresponds to each one of the motions, the steps in the motion. And the betas are going to be the degrees for each one of these motions. So here you're going to notice for beta 1, at the end of beta 1, they have 110.5 degrees. They had 0.5. We had 0.7, I think. Then you're going to notice that beta 2 is in here. So beta 2, it's going to add whatever its value was to 111.5, and it ends at 138.1 degrees. And then the next one is beta 3, and that's going to be at 210. So that's going to be then the next value. So I think beta 3 was 82.9 degrees. So that's going to be the distance here. And then beta 4 was 55.3. And then beta 5 was 82.9 again. All right. Now, as we look here, a couple things. You are going to be drawing your displacement diagrams in your assignments. I'm not going to be demonstrating it here. It would take too long. It just would. Okay. And you guys don't need to watch me do AutoCAD because you guys know how to do AutoCAD. And I don't think you need to do 4 displacement diagrams. I think 2 is enough. Okay. Josh. You will be drawing arcs and we'll show that construction in a little while. Okay. We're just kind of doing the basics right now. Now you're going to notice for your beta 1, or I'm sorry, for each one of these degrees. So since this is in degrees, how you're going to scale this out. Don't try to do this as, a multiple of 36 because you're just going to get something too long or too short. What you're going to do is you're going to say, okay, my height is 2 inches. Whatever that height is, make the horizontal about 3 times longer. So for instance, you would do 36 here, and this would be 6 inches long. Then you've got something that's 3 times as long as it is high. Okay. Use that as your guide. So that means that if this is 6 inches long, I'm going to divide that by 360. And that's going to give me the number, the distance for every single degree. Does that make sense? And then you multiply that single degree value by however long your beta is. And then that's going to be the distance that you make that beta along the length. Does that make sense to everybody? Okay. So what you are not going to do, so I hope everybody is listening. You're not going to have this super long or super short length. If your scaling along this length is really long or really short, it's going to be a 0. Because I'm telling you right now, whatever this value is, take it 3 times as long. That's what you do for the length of your horizontal axis. Got it? They don't give you that in the book here. They don't tell you that in the example. That's what I find works best. And that's what I'm telling you to do. Because otherwise, if you try to make this too long, you get a super long chart and it's really short. And it doesn't make sense. Okay. Or if you make it super long, super short. So if you try to do a multiple of 360, so if you try to make it 36 long, it's going to be really long. And then the height is going to be really short. But then if you go, okay, instead of 36, I'll do 3.6. Well, now it's going to be super short and high. So look at your height and 3 times that distance. So the height is going to be 2, your length is going to be 6, and then you just work with that. Does that make sense to everybody? So if your height is a different number, it's going to be 3 times whatever that number is going to be. Okay. All right. Because I know that's usually something that, like, where do I start? How do I do that scale? And that's a good gauge to go by. And I expect you to use that very same thing. Okay. Then the next axis that you see down here is the time. Okay. Notice that these correspond, number 1, this is the total time, the 3.9. And then each one of these times correspond to how much times it takes to do each one of those motions, okay? So your bottom scale is going to duplicate very similar to this, but you'll have different numbers for your betas and your cutoffs for each one of the motions, okay? Now, as far as the curves going in and out here, those are going to be constructed based on the type of motion that we have. We weren't quite that far here. We're going to be talking about that next. But what I do want to show you is that as we rise, notice that from 0, we're going to go up, 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 up to 2 inches. And then notice that we sit and we go horizontal for a little bit. That's that dwell. It's kind of like stay right here for however much time. I think it was 0.3 seconds. Then we're going to fall 1 inch. Then we're going to dwell for a period of time. That's where we see that horizontal flat. And then we're going to fall the rest of the way. Again, whatever we're going to go up, we have to come down. If you end up sitting like here, then you didn't add all your stuff, okay? That's wrong, all right? So your problems will have the falls equal the rises. All right, so any questions kind of as we look at just kind of the basics of what you'll construct? You don't have to construct this one. All you need to submit for example number 1 is going to be the work that we did in these first 3 steps. Step number 1 is the total time. Step number 2 is the angular velocity of our cam. And step number 3 were the individual betas 1 through 5, and then showing that they added to 360 degrees. Okay. All right. That's all that you have to do for that example. And then we're just introducing the diagram here. Okay. So let's go back. That's example number 1. Let's go back to our PowerPoint presentation. Now we're going to start looking at individual follower motion schemes. Now, as we said, displacement diagram represents the motion desired in terms of distance on the vertical axis and the angular displacement along that horizontal axis. These displacement diagrams are going to give us the graphical representation of the motion that will be used to generate the profile of the cam. So tonight we're looking at just displacement diagrams. Wednesday, we're going to be looking at generating the cam profile based on our displacement diagrams, okay? Now, they must be drawn to scale, and you will use AutoCAD. You will not sketch these, okay? There's a wide variety of motions that are available for moving your follower. There are going to be ones that are appropriate for slow-moving cams and ones that are going to be appropriate for high-speed applications. So normally what happens is you can take high accelerations if you would, and we'll see that in the diagrams that we look at in just a minute. We can use those for slow moving cams that are going to be best. High speed applications, though, we have to consider the implications of the accelerations, because accelerations, what ends up happening is they can cause high vibrations as well as the follower coming out of contact with the profile of the cam, okay? So we'll look at the different ones that we have here. Now, I'm not going to worry. I'm going to kind of breeze over this. We're not going to talk about this so much because a lot of it doesn't come into play with the equations that we use. The ones that we look at are going to be that total time, our displacement in terms of our rise and our falls, and then our betas. Those are going to be the ones that are the most common. So now there are 4 common motion schemes. They're called constant velocity, constant acceleration. And then the other 2 are harmonic and cycloidal, okay? Now, the first 2 are kind of the most simplistic, and they're the ones that are going to be most appropriate for lower speed applications, okay? So as we look here, and we look at the top of page 229, we're going to look at first constant velocity. So on the top of page 229, we have some curves here. We're going to look first at the first column here. This is constant velocity rise. Now, as we look at this top one, this is going to be follower displacement in whatever the units are, okay? So to construct a constant velocity curve, we simply are going to connect from the origin point from the beginning to where it's going to end. That's it. So this would be considered a rise, and on the right-hand side would be considered a fall, okay? Very simple construction. The only problem, I mean, it's easy to construct here on paper, but the problem with constant velocity is the fact that it's constant velocity. So when we talk about constant velocity, if we're saying it's starting from 0, well, in theory, we have to kind of speed up to constant velocity. You don't just start with constant velocity by like turning something on, right? Even though, yeah, it's pretty abrupt, but you can imagine that that creates a lot of jerkiness. It's not a smooth transition in and out. And we end up having what we call infinite accelerations at the ends, which again can cause problems with contact. So constant velocity, number one, isn't used very often because really in theory, it's not possible. Number two, you have to use it for very slow speed applications. Otherwise, you are going to have problems with contact. Okay. So we don't see it. We see it, I think, in one of the example problems just to kind of show you it. But in practicality, it's probably not going to be used. Okay. As we turn the page, the next one is going to be constant acceleration. Okay. Constant acceleration, you're going to notice, and at the top one here, this is the follower displacement. We physically see some curves going into the motion and out of the motion, which means that it's going to have more smooth operation. And we do get an improvement. Notice that when we look at the velocity curve here, it ramps up to its maximum velocity and then comes back down. Okay. Acceleration as well. Not great. There is an abrupt start and finish, but it's not infinite on the two ends. Okay. So even though the curve looks better here, we have some improvements, but not ideal. So again, constant acceleration is not going to be one that we see very often. The two that we see most often are going to be harmonic and cycloidal. The first one here is going to be harmonic. Now, this doesn't look much different than the constant acceleration one, but when we look at velocity, now we're starting to get nicer curves and smoother operation for the velocity first, and then also for the acceleration in and out, okay? And then lastly, we have the cycloidal, which is going to be on the top of page 233. Here, again, the ins and the outs are nice and smooth as we saw in the previous three, but the last, it's totally improved on velocity as we see a curve going into the velocity and out, and then the same thing for the accelerations. So these last two are for higher speed applications, ensuring that we don't have jerkiness or non-contact with the cam. Now, these are the profiles that we would see on the displacement diagram for where they're located, but how do we construct these? Okay. So when we look at construction for, I'm going to go back to the harmonic motion. This on the top of page 232 is going to be the construction of harmonic motion displacement. Okay. So how do we do this? Well, we're going to determine where along our displacement diagram that this motion is occurring. So you're going to notice that here it's starting at, if you would, the start at 0 to whatever the total time or beta would be. Okay, it's not going to be the entire length. It's not going to be the full revolution. This is, for instance, one section of. So if we look at that example we just did, if we think of that 2-inch rise, if we use harmonic motion in the 2-inch rise, we want to construct that curve. So to do that for that section, we are going to take the total distance. So for that example that we looked at, the top of the half circle here would be 2 inches. So it's a diameter of 2 inches, but we're just working with one side of it. So a half circle. Then at the center of that half circle, we're going to divide this into 6 equal segments. So 30-degree increments along that curve. Okay. Then starting at the bottom, this is going to be 0 or the start. Then you're going to have 1, 2, 3, 4, 5, 6 at the top. Then along the horizontal axis, whatever that distance might be, it's going to be different for any, different degrees, a beta 1, a beta 2, whatever it might be. And we're going to divide that length into 6 equal parts, whatever it is. It can be some odd number. We're just going to take that segment and it's going to be divided into 6 equal parts. And then the first one horizontally is going to be the 1, 2, 3, 4, 5, and 6. Now what we do is we put our number 1 vertical line up and we match it with the 1 horizontal line. And that's going to be a plot point. Then 2 is going to match up with 2, 3, 4, 5, and 6. And then in AutoCAD, you are going to put a fit spline along those lines. Okay, that's why AutoCAD is nice. You don't have to try to sketch it in. It's not going to be connect the dots with straight lines. You're going to use the spline command. Okay. So that's how you would construct it. So again, in our practice problems, we are not going to be doing this in AutoCAD. It would take me a while to go through this, and you guys have the skills. I know that you can do this, and then you're just going to do it for your assignment, and that's why during lab time, I'll be available to answer any questions that you might have. Okay, but use these as your guide. Kind of like when you get out in industry, you won't have me there, you know, to show you. It doesn't necessarily, or you might not have somebody to demonstrate for you. You got to do a little bit of research and look how things are constructed. And by what you see here, I know that you can duplicate that and adapt it to whatever the scheme is that you have. So that's harmonic motion, okay? Then the cycloidal is the motion construction that we see at the bottom of page 233, okay? Now, for this one, we are going to be breaking things into 6 equal segments again, horizontally, okay? So notice that we have the 6 equal segments for whatever the beta or the time would be. Then you're going to notice that we have our overall rise. Now, you'll notice this circle down here, and I want to call your attention to the equation for the radius of that circle. The radius of that circle is going to be equal to the overall height of that motion. So in this case, it would be, go here, the overall rise, okay? It could also be a fall, all right? But in this case, the distance that we're going to be traveling, rise or fall, is h. Then you're going to divide that by 2 times pi, and that's going to be the radius of this circle, okay? Now, as we look at the construction here, you're going to notice that from the end all the way down to the beginning, okay, we're going to extend that line, and the center of that circle for the cycloidal motion is going to be along that line, all right? Now, the next thing you're going to notice is that as we go around, we have 0, 1, 2, 3, 4, 5, and 6 comes back to that same point. So we divide this circle into 6 equal segments, which is going to be 60 degrees between each one. Now we're going to number starting with 0 and going counterclockwise around 1, 2, 3, 4, and 5. Okay. Now where they come together. So for instance, if we look at 0, 6, and 3, where they come together in the center, we're going to notice that our point 0, 3, and 6 are going to be along that line. That's going to be the point that they're on. Then we're going to see where 1 and 2 come together at the bottom, and where they come together at the center on a line parallel to the center line, where it intersects with 1 and 2 is going to be those plot points. And then lastly, where our 4 and our 5 come across, 4 and 5. Oopsie, 4 and 5. And then those are going to be the points for which we are going to be then putting our best fit spline through there. Okay. And that's how we create then the in and the out, or the in and the out radiuses of our motion. So if it calls out that you have a cycloidal motion, you use this construction. If it calls out that you have harmonic motion, you use this construction. If it calls out that you have constant velocity, which one of our examples is, it's just a straight line from start to finish, easiest construction. And then if you have constant acceleration, which you will not get in your problems or in your assignment, it would be this construction. Okay, so I really don't go over it, but you can see that it's there for you if you ever need it. Okay. All right. So those are the different types of motions and how to construct them. Lex. Mm-hmm.
Notice that the figure is off, like it's like harmonic, how it's next to.
Oh, right. Yep. So the question is, how far probably do we do that? Just so that it's kind of out of the way. There isn't a set distance. You could go closer or further away. You just don't want to interfere with the axes. Typically, because you could have one coming down on the other side, you just want to be below the horizontal axis. That's all. Yeah. You can be as.
It's not like 45.
It is not. It is not. No, because this angle is going to be dictated by how long this is, right? And what the height is going to be. So that's going to come, and then you just go extend that down below, and then that's going to be your circle. Yeah. So good question. Yeah. No set offset or distance between there, because wherever we go along there, it's gonna not affect really where those points are going to intersect. Any other questions before we move on? Okay. No, just this area, just this area. So whatever the prescribed motion is. So notice that this says either the total time or the beta for that corresponding. So if we remember back over here on our example problem, we had 5 different betas. So we're just looking at one of these sections here. And we're going to divide this into 6. Does that make sense? So if I do a harmonic motion on this side right here, I divide this into 6 sections, right? And then for this section right here, this would be in 6 sections. I would just work with whatever that prescribed motion was, that one beta. Okay, and then I have a dwell that would be just a straight line, no construction for that. And then you're going to notice over here, now I've got another one. So this would just be for this section. So we would have it for just that area. And then this would be, if you would, that would be harmonic. And then you would just work with that beta. And that would be 6 sections within that area. Yeah, so notice on each of these constructions, it's only in reference to a single step in your motion, if you would, of the whole revolution. All right. Okay, so we're going to look at an example. I think that's coming up. Yeah, we looked at harmonic and cycloidal. So we have 2 examples that kind of go hand in hand. Okay. Example 2, 9.2 and 9.3. So in example 9.2, we're just going to do the first 3 steps. And then in example 3, we're going to look at the displacement diagram and how it corresponds. Okay. Neither one are we constructing or drawing in AutoCAD the displacement diagram, which I know is going to be fine. You'll get 2 and you'll get a good idea of this. Okay, so let's look at problem 9.2. Now, again, we're just going to do the first 3 steps here, and there's part of this that we're not going to do that they did. So a cam is to be designed for an automated part loader as shown down here. Okay, so notice the cam is on the end of the motor, and it is connected to this arm right here, and it's going to move this going back and forth, in and out. Okay. So it says, what we want to do here, it says, using the motion equations, construct a chart that tabulates the follower displacement versus time rotation. That is what they did over here. I have that crossed out. We are not doing that. Okay, we're not doing that. What we are going to do is we're going to plot a displacement diagram in example 9.3 to correspond to this. Now, let's look at what they have for our motion. Step number 1, it says we're going to rise 50 millimeters in 1.5 seconds using constant velocity motion. Number 2, it says we're going to return in 2 seconds, which means that we're going to do that full 50 millimeters in 2 seconds, but this time we're going to use cycloidal motion. So on the rise, we're going 50 with constant velocity. On the fall or the return, full 50 millimeters, we're going to take 2 seconds and use cycloidal. Then we're going to dwell for 0.75 seconds. And then after that, we're going to repeat. So that means that 4 is not part of the sequence here. We just have 3 steps, if you would, in our motion: a rise, a fall, and a dwell. Okay. So the first step, just like it was in example 9.1, is we're going to determine what is the total time that we need for this particular motion or sequence of motions. Okay, so we're going to start off here. Example 9.2. And step number 1 is we're going to add up. I pressed too hard. We're going to add up our times for our total time. So like we said, we have 3 steps. So we're going to have T1 plus T2 plus T3. So we want to put each one of those in here. So the first time is going to be 1.5 seconds plus 2 seconds plus 0.75 seconds. So our total time, what do we get for that? 3.5 plus 0.75, is that 4.25? 4.25 seconds. Okay, that's going to be our total time for all of this motion. Okay. All right. Then step number 2 is we want to determine how fast is this cam rotating. So we need the W of the cam. Okay, and that's going to be equal to 1 revolution divided by the total time. Okay. So if we look, we're going to have 1 revolution on top, and our total time from above was 4.25 seconds. So our cam angular velocity, what does it come out to start off with in revolutions per second? What do we get? 0.2353, correct. 0.2353, and that's revolutions per second, right? And we'll be using this revolutions per second, we know, to do our beta later on, so we'll kind of keep that up there. But to report it, we want to change this to revolutions per minute. So we're going to multiply it by 60 seconds. The seconds cancel. So our cam rotational speed and revolutions per minute should come out to be about 14.112 RPMs. Bless you. And this would be something we would, here's the angular velocity of our cam. Okay. And then our step number 3 is going to be calculating our individual betas, our beta 1, our beta 2, and our beta 3. So let's do the first one together. Beta 1 is going to be equal to the angular velocity of the cam. I am not a mechanical pencil person. Times T1. So if it's beta 1, we want to multiply it by T1. So we're going to take this time the 0.2353 revolutions per second. And we're going to multiply that by T1, which was 1.5 seconds. 1.5 seconds cancels. And I think we're going to get our beta 1 comes out to be 0.353 revolutions. Now, we want to convert that to angles, or to degrees, I should say, how many angles we're going to be using. So we're going to say 1 revolution is 360 degrees. Revolutions cancel out. And what do you get for beta 1? Yep, 127.1 degrees is equal to beta 1. So this is going to be our first chunk on our displacement diagram. Then we're going to do the very same thing for beta 2 and beta 3. So go ahead and calculate your beta 2 and your beta 3, and we will compare in just a second. And you can check in the example to see how you're doing on each one of your betas. And then make sure that you do a check. Beta 1 plus beta 2 plus beta 3 to make sure that they equal 360 degrees. And if I do that, and mine do come out, so I got those values there for each one. So I'll give you a chance to make sure you get the same values. So did everybody get their values to come out so that you have 360 degrees in betas, 1 through 3 equals 1 revolution? Any questions at all on your values? So this is my beta 2, beta 3 is here. Okay. All right. Now, this is what you're going to hand in for example 2. Okay. Now what we want to do is we want to look at, we're not going to do the tabulation that they did, but we're going to turn the page and I'm going to do a little bit of erasing here because I want to be sure that you kind of see the construction here and how we're doing it. Okay. Okay. So now example 9.3 wants us to create the displacement diagram for example 9.2. Okay. So as we know, it said that we had those 3 steps. We had a rise of 50 millimeters in 2 seconds. We had a fall of 50 millimeters in, what was it? 2 seconds. Oh, wait a second. This was 1.5 seconds, beta 1. Beta 2 was 2 seconds. And then 0.75 seconds was the tail end. Now we figured out each one of our betas. So we have beta 1 as 127. We had 0.1 degrees. Beta 2 was 169. They have 0.3. I had 0.4. And then they had the last 63.7. I had 63.5. As long as you're within decimals of the degrees, you're in good shape. Okay. And when you add them together, you come up with your 360, which I did exactly on the dot. Now, for the first section here, you're going to notice that they have this laid out. Now, again, scale. So you'll notice that you have 50 millimeters on your rise. That's going to be the y-axis. So that means that you are going to make your x-axis, your total time, 3 times as long. So that means that this is going to be 150 millimeters long. Okay. And then from there, you know that if I kind of put the end here, this is our 360 degrees. If I divide 150 by 360, that's the distance I would go per degree. Does that make sense to everybody? So then if I want to know how far beta 1 is, I'm going to take that value per degree and I'm going to multiply it by 127. And that's going to then be the distance that would represent to scale the 127 degrees there. Does that make sense, everybody? Okay. All right. Once I have that marked off and I know that that is where I am ending. So the start is going to be at my origin here. My ending is here. Remember, this was constant velocity. So to construct this, it's as easy as starting at my 0 and ending at the top. That's it. Okay. You don't get to do one that easy for your assignment, but that's okay. But on the fall, it's going to be cycloidal. So you can see how the construction of the cycloidal is here. You will be showing the construction of your of any of the harmonic and the cycloidal for the problems that you do. So down here at the bottom, you're going to be handing in one calculation for this example, and that is going to be calculating the radius of that circle. The radius of that circle is going to be the height or the rise. And it's going to be divided by 2 pi. So, for example, 9.3, our radius is going to be equal to our h1 divided by 2 times pi. So the height of the rise, or in this case, the fall, is going to be 50 millimeters divided by 2 pi. What do you get for the radius of that circle? 7.96, yes. And that's going to be millimeters, okay? This is all you hand in for this example, all right? But now let's talk through the process here to construct this. So first of all, you are going to create a circle from the top to the bottom of your beta. So remember, this is going to fall in 2 seconds or in 169.3 degrees. So you're going to mark off how wide that would be in distance, right? And then starting at the top here to the bottom, you're going to draw a diagonal line going all the way to the bottom, and then you're going to extend it. And this is where the center of that circle that has a radius of 7.96 millimeters is going to land. Just make it down below that horizontal axis, so it's not like interfering with that, okay? Then what you're going to do is you're going to mark off so that you have 6 divisions, so 60 degrees in between each. The top 2 are going to correspond to these guys over here. So this would be like your 4 and your 5. Your 1 and your 2 down here is going to correspond to these 2. So this is like your 0, 1, 2, 3, 4, 5, and then 6, going backwards. And then your 6, 3, and 0 are going to be along that middle line, okay? And I forgot to say, I should have said this first. You're going to break these into, this would be your 6 equal segments. So this would be 0, if you would. This would be 1, 2, 3, 4, 5, and then this last line would be 6. And then down here, these 3 in the middle here, you're going to have a 0 and a 6. And then this is going to be 3. This is going to be 1. This is going to be 2. This is going to be 4. And that's going to be 5. And you can kind of see, I mean, it's kind of silly for me to talk through what each one of those lines. You can see what's happening there. And you would duplicate the construction in CAD. Then once you get your crossover, your line intersections, you're then going to use the best fit spline to create that curve, okay? And then the last part of the motion is going to be the dwell, which is just going to be down at the baseline there for a straight line to 360 degrees. Yes. Just that it doesn't interfere. So you can't put it here, okay? It has to be just down below that horizontal line. The angle does matter. The angle is going to come from where this starts and this ends, and then it's going to extend. Yeah. So yeah. And so depending how wide or how short that is, that angle is gonna change. So it's not like a 45-degree angle. It's going to be whatever this distance is from the start to the finish of the beta, from the top to the bottom, it's going to be that line extended down. Okay. Other questions as you look here? And I'm certain that as you look at this and as you start creating it, there will be questions that crop up, and that's okay. That's okay. But use the construction here, the examples, as well as the information in the book as a guide, because it's good. It really kind of lays it all out. Okay, so we're not going to create this in no CAD diagrams for the practice problems, just the work that we just did in pointing out. Okay, so to review for the practice problems for examples 9.2 and 9.3, for 9.2, you're going to do those first 2 steps, the total time, the cam rotational speed, and then each one of the betas with the check at the end to 360. Then for example 3, it's just going to be the radius calculation. All right. And then again, we talked through how to create that displacement diagram. So now that kind of brings us to the end of what I was going to cover tonight. You would be ready to do the first 2 problems in assignment number 7. So if we look at And we do have more to do. The next time we get together, we're going to be looking at the CAM profile. But we are going to look at assignment 7. So our first two problems are 9-7 and 9-9. Those are going to be creating displacement diagrams. And you're going to find those on page 254. Okay, 254. Now, for 9-7, says we have a cam drive is used for a mechanism that tests durability of oven doors. The cam follower must rise outward 2 inches with harmonic motion in 1 second. Okay. Then it's going to dwell for 0.5 seconds. Then it's going to fall 2 inches with harmonic motion in 1 second. Then dwell 1 second. And then it's going to repeat the sequence. So there's 4 steps there. Okay. 4 steps. Determine the required speed of the cam. So that's going to be your W of your cam. And then determine and graphically plot the displacement diagram. So you're going to do those first 3 steps. You're going to do the total time, the angular velocity of the cam, and then you're going to do your betas for each one of these. You're going to have a beta 1 through 4. And then you're going to create a displacement diagram. Now, because it's harmonic motion, you are going to look at page 232 at the top here. This is going to be how you construct your rise and your fall. Okay. So whatever the total rise is, that's going to be the height of your half circle. You're going to divide that into 6. And then whatever your beta is going to be the length of that line. You divide that into 6 equal segments. And then you find your corresponding points, and then you put a spline, a best fit spline through those points. Okay.
So are we designing this in AutoCAD tonight?
Whenever you want to draw it in AutoCAD, but it will be in AutoCAD, yes. Now,
right.
As far as what is included and what you have to put for your diagram, use the illustration right here for what you have to put on each one of the axes. This curve is going to look different because it's going to be a different motion, but as far as how you label the axes and what's included in each one, this is what I want it to look like. Okay. Yes, it's going to take some time, but it has to be done in AutoCAD, not sketching. Okay. So that's your first displacement diagram. Your second displacement diagram is 9-9. Let's look at what that one says. 9-9 is a cam drive is going to be used for a mechanism that packs stuffing into shipping boxes. The cam follower must rise upward 1 inch with cycloidal motion in 1.5 seconds. And it's going to fall 1 inch with cycloidal motion in 1 second. Dwell for 0.5 seconds and then repeat. So this one has 3 steps. Okay, a rise and a fall and a dwell. Determine the required speed of the cam, the W of the cam, and graphically plot the follower displacement diagram. Okay. Now, for this one, the rise and fall are 1 inch. For the other one, the rise and fall are 2 inches. Okay. So remember your scaling. If you're rising for 2 inches, how long is your y-axis or your x-axis going to be? How long is I'm sorry. If your y-axis, your height is going to be 2 inches, how long is your x-axis? 3 times as long, 6 inches. Yes. So for number 9, if your rise is 1 inch, how long is your x-axis? 3 inches, 3 times as long. Yes, as your whatever your height is. Okay. I don't want super long x-axes or super short. If you don't do them proportionally, I'll know you weren't listening and the question is a 0. I don't care if the construction is correct. The proportions are 1 to 3. Okay. All right. So any questions? I know some will come up, and that's why lab time is really important, especially for this, because I'm not demonstrating the CAD. I know you have the CAD skills and you don't want to sit here and watch me do AutoCAD, right? That would just make our lecture probably 2 times longer, and they're long enough. They're long enough. Okay, so that's all that I'm going to go over tonight. So I will stop the recording here. Don't go anywhere if you're virtual.